I hope everyone's doing well. I am Mr. Ish. Thank you for joining me for this video. The arc length of a circular arc is equal to r theta. You know this formula, you've seen it. Why is this formula the way it is? How can we validate it using calculus? And that's the purpose of this video. At its most basic level, a sector which will demonstrate a certain arc length has a certain angle theta, but this is representing a certain portion of a whole. This arc length is a portion of a whole, which is a circumference 2 pi r multiplied by a certain factor theta, and you know whole circle is 2 pi in terms of radians, theta over 2 pi, and you easily get r theta as being the arc length. But this is such an easy geometric procedure and there's nothing wrong with it. But can we use calculus, integral calculus, to validate it? We can. I'll show you. Our representation will begin with this, and you know the arc length formula. Lower limit, upper limit, square root 1 plus your derivative square dx. You would think simply running through this arc length formula would bring us the r theta. It's not as easy as it seems, because the problem is the limits we have to bring a and b. That right there ends up being the hardest part of this entire exercise. When you look right here at a representation, here's my arc length. But this arc length is a portion of a whole, and what's that whole? It's a unit circle centered around the origin. X square plus y square is equal to r square. You solve for y is equal to square root of r square minus x square. You've seen this so many times that you know this by heart. When you have to do the derivative of this, you know again this because you've memorized it. And the derivative of anything which looks like this would be something with the x square coming out as a minus 2x, and this here as a 2 root r square minus x square. You can do the chain rule and easily do this. The 2's will cancel out and your end result is a minus x divided by square root of r square minus x square. You can easily do this and there's nothing hard with it. But the formula requires us to bring in the square. When you do the square of this, you're looking here at an x square divided by r square minus x square, and we have to save that. Now let's look at the limits, which is the hardest part. When I look here at this and I bring it down here, I'm looking at a certain upper limit, which is b. At this point, I'm looking and bringing it down, I'm looking at a certain lower limit, which is a. But look, I've generated two right triangles. Here's one right triangle right here. Here's another right triangle here. If you bring out this entire representation, it looks something like this, and you have another representation like this. That's what it is. From here to here is your b dimension. From here to here is your a dimension. You have a certain angle over here. I'll call this angle, we'll call it theta 2. We have a certain angle here, we'll call it theta 1. The difference of these two will give you the angle of your sector, which you know happens to be this angle right here. That'll be your angle theta. And these representations can change based on the nomenclature you want to use. But look, everything stems from this fact. When I'm looking at this larger or flatter triangle, which is theta 2 and a b, I have a certain r. I need to start determining my limits. What do I have here? Cosine theta 2 is equal to b over r. b is equal to r cosine theta 2. That'll come right over here. I'll just save this for right now. When you look at this more vertically inclined right triangle, you have an a, you have a certain angle here, theta 1, and you have an r. Here I'm saying cosine of theta 1 is equal to a over r, and a is equal to r cosine theta 1. What I'm going to do is erase some of this for you, because I've done the work here on the bottom, and all you have to do is bring that item in terms of your limits. Again, the limits are the hardest part of this exercise. When we have this formula, this is what is coming through. A is equal to r cosine theta 1. B is equal to r cosine theta 2, and then we have all of this coming in here. Now this part right here, dy over dx, actually, you know what, let's erase this. Let's consolidate all of this. You have everything over here, and I'm doing a little bit of a change over here. I'm writing this as a, this as b as my reference. Now look, this part right over here in the root, I'll have a 1 plus x square over r square minus x square. When you do the algebra over here, you'll have a r square minus x square plus x square divided by r square minus x square. These cancel out. You'll have a square root of a r square divided by square root of a r square minus x square. You'll have a r divided by square root of r square minus x square. And you've seen this many times, so why don't we just bring that in directly over here? I have here an r divided by square root r square minus x square dx. If you want to do another change, this r, a coefficient, you can bring it right over here, r, and you can bring this dx over here, and everything looks good. here in terms of a denominator and this. We have a trigonometric substitution which is coming into play. A certain value a I'm designating as that is equal to the square root of r squared, which is equal to r. A certain x is equal to r sine theta. A certain dx, the derivative, is equal to r cosine theta d theta. Because everything here is of the a square minus x square form of trigonometric substitution procedure, now we need to worry about these. I'm not writing theta 1 and theta 2 because I have a theta 1 and theta 2 here. To avoid confusion, I'm doing a different terminology. I'm doing a theta prime and a theta double prime. Not to be confused for derivatives, but it's just a distinction and it's just a representation, nothing more than that. Everything coming into place of this. I have this r cosine theta 1 is equal to r sine theta. When you push the r onto the other side, it will cancel out with that. But when you solve for this specific angle theta, which is what we're solving for, to get this value, I'm getting here a arc sine of a cosine theta 1, and that's what it will be, arc sine of a cosine theta 1. Now you will do the same exercise for the upper limit, and we will do so. The upper limit here is r cosine theta 2 is equal to this right here, r sine theta. You again are solving for this. The r's cancel out. This angle theta we're solving for, now being represented as that, is equal to arc sine or inverse sine cosine theta 2. And that's what we have, arc sine cosine theta 2. Why do we have to go through all of this technique? Because in that initial representation, I don't have numerical values for a and b. Everything is coming out using right triangle trigonometry. Now what we have is this, s is equal to r, and now we have these limits coming into play. Arc sine cosine theta 1, and then we have arc sine cosine theta 2. Look at this entire box portion right here. We'll work on that right over here. A dx is equal to r cosine theta d theta, and this you have here r square minus x square, which is a r square sine square theta. You've seen this so many times. You know, looking here in the root, you're looking at an r square into 1 minus sine square theta. By means of the trigonometric identity, sine square theta plus cosine theta equals 1. The cosine square theta is equal to this. So you can even substitute it in, and now you're looking at a square root of a r square cosine square theta, which is a perfect square in a perfect square root. When you do all of this, you're getting from here just an r cosine theta. This r cosine theta will fully cancel out with that, leaving only that. And that's the only thing which remains here in terms of what will lead to your antiderivative. When we're doing the antiderivative of this, I'm not writing my antiderivative as theta because I don't want to confuse the antiderivative for what I'm trying to bring about in terms of the formula. So I'm bringing yet another item. I'm calling it a theta prime. It's just a designation. I have an r sitting outside. This right here is my antiderivative. I'm designating as that. I have an arc sine cosine theta 2, and I have an arc sine cosine theta 1. Now, do you need to see this part over here? No, you don't, because you've seen the end result of that part, and I've written it for you right here. You're doing the upper limit and the lower limit and the difference of the two. You are looking here at an arc sine cosine theta 2 minus your lower limit arc sine cosine theta 1. This right here represents a legitimate difference of two angles. That is in terms of a single angle, and I'll tell you what I mean. When you saw that representation at the very beginning, it was something like this, and you know it to be the case. You had a certain angle here and you had a certain angle here, and the difference of these two angles gave you this angle right here. That's exactly what we're talking about. That's what I'm referring to here. This right here can come in by means of a substitution. Let theta here equal to this right here. Your theta double prime minus theta single prime, which represents what you see over here, arc sine cosine theta 2 minus arc sine cosine theta 1. This here being my theta double prime, this here being my theta single prime. And then when you bring in that substitution, you end up seeing s here is equal to r theta, and your procedure comes to a complete. If anyone feels that there's a doubt in this procedure, allow me to eliminate that doubt for you. You can do so by means of a representation with regards to actual numerical values, and I'll show you here only in terms of an exemplification procedure. This is what we're trying to determine right here, theta. I had a certain angle over here and I had a certain angle here. Let this angle here, theta, be equal to 20 degrees. Let this angle here, theta, be equal to 70 degrees. And this right here I was calling theta 2, and this here I was calling theta 1, as you saw from the earlier representation. Anyhow, plug these values in. Right here I have arc sine of cosine theta 2. I have arc sine cosine of theta 2, which is 20, minus arc sine of cosine theta 1, which is 70. And you'll see the difference of these two in terms of the computations will be 50 degrees. And I'll show you by means of a calculator. You can do everything here on the DEG mode. Don't even worry about the RAD mode. Look, 20 cosine, everything on the DEG mode. I'll do cosine and I'll do inverse sine because it's an arc sine. I have a 70 coming from right over here, minus. And we can do that. Cosine 70 and we'll inverse sine it. I have here a 20 coming out of it. And what's the difference of these two? 50. And then you would convert this into radians easily and then run it through this formula right here, r theta, and you'd have everything. So this procedure is exactly 100% right. I've shown you by means of these substitutions, r theta is equal to arc length. I have just used different items over here in terms of representations, theta prime, theta double prime, and I was using a theta triple prime as you saw in part of the procedure. Anyhow, we're done with this exercise. S equals r theta, and we validated it for you. Thank you for watching.